Ah, okay. I would love to ramble a little bit more, but we kind of have to get to the point. Because I am here to pry some knowledge out of your hands. Uh, so I was thinking that perhaps you can tell us a little bit more about thermally compensating Class A amplifiers, because the first watt projects that are widely available for the wires, they will have power MOSFETs in the output stage, but unlike most of other amplifiers projects, they do not feature like a active bias spreader transistor that is like a sensor of the temperature. And I was thinking if you can maybe tell us a little bit more, how do you do it, that your designs are thermally stable? And maybe let's start with F5.
Well, the first thing that people need to understand is that in order to make transistors do their job, you have to run some current through them.
Yeah.
And it has to be, most of the time, it has to be some kind of standing current that's going through it, even when it's not actually reproducing signal. It's not a rule that it has to be, but it's very difficult to get performance out of it unless there's some kind of a river that's already flowing, and they call that bias current. For example, well, not for an example, you have to understand that there are any gain device, okay, and this could be tubes, or it could be FETs, or it could be bipolars. There's a limited number of ways to use it. And you've got three, in the simplest model, you got 3 pins. And in the case of a FET, which is a fine example, it's the drain, the gate, and the source. And current that's being amplified goes from drain to source and is controlled by what's going on to the gate, which is not current, but voltage versus the source. In a bipolar transistor, it is the collector to emitter. That's where the current flows, and the base is the control pin. In a tube, which is the first example you would want to think about probably, you have the cathode is the equivalent of the source. There is a brain farting on tubes here. The input terminal, which is the I can't remember. Like, I forgotten what pins are used on tubes. Let's see. We've got the cathode, the anode, and
the grid.
Pardon me?
Grid.
The grid. I was thinking grid, and I went, "That's not it. That's not it."
I had to say. It's like, no.
You can tell. You can tell how you.
Yeah.
It's not help me ever. Anyways, in that case, the grid is the control pin. So you've got. There are basically 3 ways of using those devices, both the FET and the bipolar transistor and the tube. And the control pin is the element that, relative to, in the case of a MOSFET, the source, controls the amount of current going through it. In the ideal case, all 3 of these are kind of very, very similar. There's 3 ways of running them, and in the case of a MOSFET or any FET, it is known as a common drain, common gate, or common source. And mostly you think in terms of that's the pin that is hypothetically grounded. It may be at a DC potential, but it's not carrying signal as such in terms of voltage. So common drain is a follower, where you put some power voltage on in this case, the drain, and it's the relationship between the gate and the source that determines how much current goes from the drain to the source. And the same thing is true of tubes, and is true of bipolar. So they're all real similar, but there's some obvious differences. Common source, common gate is and actually what they think of as more like a cascode operation, not particularly useful much of the time. And then there is that's common gate. Common source gives you voltage and current gain. Again, common drain just gives you current gain. All of them, to give you a low distortion signal, have to be at some operating point, which it means that there's current already flowing through the device, just like, it's a river. And what we're going to do is divert portions of the river to do some other job with, here's our dam, and this is the spillway where we want to go somewhere else with it. And the class of operation comes down to a description of how are you handling that standing current. In the case of class A, the river is always flowing, and you modulate the amount of current that goes through it. It gets less, it gets higher, but it doesn't shut off. In the case of class AB, you have a push-pull operation where there's two gain devices, and one of them is doing more work than the other. I'm sorry, you can make class A with push-pulls also. But in class AB, you've got two devices, and one of them does the load and then switches over to the other one so that this one does the plus current and this one does the minus current. And to give a really clean transition between the pluses and the minuses, you've got to have that standing current. And class D, well, that's a whole other category.
Yeah.
There's no standing current as a concept. So the issue comes down to largely the performance of these of the control pins versus the device and the current goes through it is dependent on the temperature of the device. Not so much with tubes, although there's some dependency, but in the case of bipolars and FETs, there is considerable dependency. Bipolars being the most dependence. You have to make up some means of either stabilizing that passively by, for instance, putting some resistance in series with, in the case of bipolar, the resistance in series with the emitter so that it kind of impedes the flow of current a bit so that it stabilizes. In the case of a FET, similar sorts of approach, you do that to the source. You don't really want to do that all that much because it's in between the transistor and say the loudspeaker that you're trying to drive, and so it's literally it's in the way, but it keeps the transistor from going haywire with too much current just idling through it, because they heat up, and as they heat up, they start doing more current, and so on. Not true of tubes, not true of all semiconductors, but very true of your average MOSFET, or and also very true of your of any bipolar. So you have to compensate this in some way. Typically circuits that set up this current, they're called bias circuits. They set up the bias current, which is that standing amount of flow, and they will have temperature compensation built into them one way or another. Sometimes what they do is they use the same kind of device conceptually, and as it warms up, being next to the transistor that's getting hot, its character starts conducting more current and takes away from the control pin that's driving the big device, and so it can be used to compensate. And that's true also of again, FETs. There are some FETs that actually do less current when they heat up. So, sometimes you might even have to conceptually adjust that, but usually not. Those kinds of parts are usually so nicely stable on their own that you don't spend a lot of time worrying about them. No, but it is important to stabilize that, or it'll either run away and burn up, or if it wanders around, your distortion characteristic, the distortion which is suppressed by having the right amount of current going through, particularly push-pull stages, where the two halves of an amplifier, plus and minus, are sharing that current. They need to get along real well. There are specific currents that are excellent for that. Usually more is better, but too much is also a real problem because it'll run away. So here you are with bias circuits. for Class AB push-pull and also for Class A push-pull, normally you better have one, and there are only few devices types that don't require them. But it's just a little voltage source. It's usually a transistor and a couple of resistors.
Mm-hmm. And because you mentioned the resistance in the source before, so I understand that the more current flowing through the transistor will create more voltage on the resistance, in effect lowering the effective voltage driving the transistor, which creates the regulatory solution. And that's exactly how it works with DF5, doesn't it?
Yes. In fact, just about all of the push-pull circuits that I have, there's a few that don't have such things. Mm-hmm. But something like an F5 is a fine example of a push-pull circuit where there is some what we call source resistance between and those output transistors there, which they're known as common source configuration, and that means that they have both voltage and current gain. And their sources either talk to ground on the minus side or onto the positive side, mm-hmm. and they act like brakes. And you have to put extra drive to those transistors to get them to put out more current, but the drift becomes very low. Mm-hmm. Mainly, in the F5, for example, it is just set arbitrarily low such that the transistors will heat up to a point where they're increasing for a little bit, and then they hit that point where the resistance on the source becomes more of a stabilizing influence, and then it settles in. This would be something where the amplifier likes to warm up a little bit. It'll run coming out of the gate cold, but if you give it 5-10 minutes, it'll fall into a pattern where it's that it was designed for.
I see. And if somebody would like to build their own version of this device and perhaps using different FETs, and can you give us any advice how to find the source value for the value of the source resistor to reach that equilibrium?
Yeah, how you usually do well. First off, there are ways that you can do it without a source resistor, and there is. I have, for example, versions of F5 that have no source resistor at all, but what I do is I have a drain resistor that senses that current at the output between the two halves, and gets fed back to the input stage and lowers the amount of current there so that it doesn't drive the power transistor so much, so that it balances there. There's an advantage to that, and that is that in particular in the case for power MOSFETs, you have what is known as a square law characteristic. That is to say, current going through the device from drain to source is a square function of the voltage that's driving the gate to source, so that if you, for instance, raise that voltage by 10% going at the gate, you will see maybe a 15% increase in current, so that it's not proportional. And so the when you look at the relationship of current, voltage across gate to source versus current, it's not a straight line, it's a curved line, and it forms, roughly speaking, a square law. In square law, you double something and you get 4 times as much. Yeah. This isn't exactly that, and there are limits to this, but there's a lot of it. Square law has some nice little charms on its own. One is that one of them is that if you have 2 square law devices operating in opposition to each other in Class A, their curvatures tend to cancel very nicely, so you get a much lower distortion number. Right off the top, that's every reason to do it that way. If you're putting resistors, on the sources to stabilize the bias, you find that it's less so that you don't get as low a distortion figure. You also don't get as low as you don't get as high a gain either. So you're putting brakes on things, but to stabilize stuff. In the case of square law, though, it's really desirable to have that in a push-pull circuit because of this distortion cancellation that it gives you. It lowers the distortion by quite a bit. The other thing that it does is it allows when you're running class AB or class B, you have one side is doing the work, and the other side is at some point is shut off beyond a certain current. It's shut off, and then you've got to, when you come back around to the other half of the waveform, now this one's got to turn on, and that one's going to shut off. Well, there's a kind of a glitch associated with that, and there's a little bit of a time delay, and so you have crossover distortion. You have, and you've lost the. That's why we run Class A for the most part. Is that it gets past all of those issues and makes things all nice and smooth.
Yeah.
The distortion gets lower and lower as the signal gets lower and lower. With square law, though, you get enough cancellation that you already lowered the distortion quite a bit. But the other thing is that square law gives you an overlap of conduction that is beyond that of just the bias current itself. In other words, if it were perfectly linear and not a square law function, then there would be this sharp discontinuity between the two parts, plus and minus, when you hit that region. And of course, where you'd be enjoying that the most would be at low levels, not at very high levels. So if you're doing concert work at a PA, a Class B amplifier might be a perfectly acceptable thing. If you are sitting in your home with an efficient pair of loudspeakers, maybe not so much, because this is a problem that shows up worst at lower levels. However, the square law extends the Class A region. Normally, the Class A region would be something which is limited just to the size of the bias. If it's a 1 amp bias, for example, and now the positive half is suddenly going off into more than an amp, then negative side is shut off, and vice versa. With square law, though, you can extend that window where both devices are conducting for a given bias current, and you routinely you can take something like improve those figures by about 50%. For example, twice as much power, and yet it's still Class A. Beyond what the bias current had asked for. So you get this smooth transition at a higher level because it's a square law part, and because you didn't use a lot of source resistance on those power transistors, because they kind of spoil that square law effect, because they were a non-square law element in series with. So it's fun. It's one of the reasons I really like FETs. And also tubes, but it's hard to do push-pull tubes and play these same tricks. But with FETs, you really can do that. And with bipolars, it's not so much, because it can be done, but it's far more delicate proposition. So with FET, there's a lot of advantages in terms of the simplicity and the ability to play games like this with the square law, and you just get performance with less effort.
Yeah, I see. What you described is probably something that works in the F7, doesn't it?
Yes. Well, if you look at anything I've done for the last 20 years plus, longer, 30 years, is FET, some kind of FETs.
Yes.
Like, I don't occasionally do bipolar, but to me, it is. It's more entertainment now. It's not. It's not what I'm seriously pursuing.
I meant the lack of source resistance. That's what I meant with the F7.
Yes. Well, the F7 enjoys one more thing. When I mentioned that MOSFETs and everybody all have these temperature dependencies, there are exceptions, and what are known as lateral MOSFETs are a very excellent exception. Wait a minute.
It's okay. I'm alive.
I always go running off to go fetch things. Now,
I also have everything here, but
let's see. I can't quite catch the focus on that.
uh
Is it an MOSFET?
yep, it's the one from you. Thank you.
Oh, yeah. Okay. Well, that's what I used. And those were, they aren't bad. At the time I got that was about all that was left on the market. And the Hitachi used to be the outfit for making lateral MOSFETs. I do have one of those in my collection. But in the case of doing stuff for the first watt F7, I found that Allfet was making good complementary lateral FETs. So I used that. And it's the laterals are good because they had low temperature dependency, so that the bias might wander a little bit, but it doesn't run away. So they warm up a little bit and they reach a temperature, and then they go, oh, okay, that's nice. That's where you set them. They don't go running away on you. So you can run them undegenerated, which takes real advantage of the square law phenomena that I discussed. It's not perfect, and that it comes from the fact that laterals, while they don't need to be degenerated, and they are not very temperature dependent at all, in spite of that, they also though have somewhat lower gain. So the world doesn't necessarily go jumping into laterals offhand, because of the fact that the transconductance figures are lower than you can get with the other kinds of MOSFETs, which are referred to as vertical MOSFETs. So it depends on what you're doing. But if you're building push-pull Class A amplifiers and you want to spend the money on laterals, that's a good place to do it. And at this point, I'm not sure what laterals are on the market.
Hexagon.
Pardon me?
Hexagon.
Oh, yes, that's right. I
Yeah,
forgot.
they're still available.
We're forgetful today, let me tell you.
Yeah, I remember Alphabet being available at DigiKey and Mauser like this.
Yeah.
And they just disappeared. But Hexagon is still available. I think their distributor Profusion has still like thousands of them. So,
well, and they're excellent parts.
Yeah, and they have an exact replacement for the 08 N16 and the P16.
Well, recommended highly. The F7 was a very interesting amplifier. It is much like an F5, except that it's executed with laterals. Another difference to that was that it also used positive current feedback. There was a sense resistor at ground on the other side of the loudspeaker that would tell the amplifier how much current was going through the loudspeaker. That voltage could be fed back positively to the input. And what it did effectively is it was a positive feedback, but because it was sensing current, what it did is it provided extra drive as the current increased through the load. What that gave us was a very high damping factor. In fact, the damping factor could be, well, you can theoretically have an infinite damping factor. You can then have imaginary damping factor.
Yeah.
But I didn't choose to head off in those directions because I wasn't trying to be crazy. What I was trying to deal with was the low transconductance, the lower gain of the laterals didn't give me didn't give me the opportunity to have enough feedback to get the distortion down to the numbers that I wanted. And then of course you can always add more gain stages, and you can always play more other tricks, but inevitably it's more circuitry. And all I really wanted was a little more damping factor because it wasn't enough damping factor for me. So I went with that little trick, and it worked out great.